All right. Next problem. What we'll do is we'll just say that we've got a painter. He's got a ladder here. He's got a ladder here. He sets up a nice thick board. And we'll give this board some dimensions. Let's say that this board is 5 meters in length. Probably pretty large, but whatever. We're going to put the painter somewhere on the board here. Let's put him here. And let's call that distance 3 meters. Now, if we're looking at all the forces acting on the board itself has weight. Alright, so we're going to have to give the board some mass. Let's say that the board is 50 kilograms. Let's make the painter 75 kilograms. The board's weight is going to be directed at its center of mass right there, halfway across the board. So that would be 50 times 9.81, which ends up being, not that, 490.5. Right there. So we know what force is being applied to the board. We know exactly where it's being applied to the board. Now there's a person standing on the board, and essentially what he's doing is he's pushing down with a force equivalent to his weight. So the force acting on the board by the person is going to be directed right here, and the person is 75. So 75 times 9.81, what we get is you get 735.75. All right. Now, you got two forces pushing down on the board. They're being supported by these ladders below here. And basically what they're going to do is they're going to exert a normal force here. You got a normal force here, and you got a normal force here. And they're not equivalent. So we're going to call them N1 and N2. In fact, anyone that's been, would carry an object with an uneven weight distribution would know that it's probably harder to hold it up here than it is here. I would expect this normal force. I would expect this ladder to be supporting a lot more weight because the person's closer to it. But right now, when we look at this from a static equilibrium standpoint, you don't have any ability to find out those normal forces. I do know that the net force on the board is equaling 0. It's not moving. N1 is pushing up, N2 is pushing up. You got your two forces down, which are 490.5, the weight of the board, and the person pushing down with a force equivalent to its own weight, 735.75. You got two unknowns here. So you can't solve it using this expression here. This is where we bring in a rotational equilibrium concept. A lot of people go, why would I think about rotation when this object is not going to rotate? And that's exactly why you would want to think about it this way. Because it's not going to rotate. So it has to be in rotational equilibrium. So what you can do is you can define a pivot point. And if you choose your pivot point carefully, you can completely eliminate one of these forces from the expression here. So if you take a look at this, let's just for the sake of argument define this as our pivot point. What that does is that makes this force generate absolutely no torque at all. This will generate torque, this will generate torque, this will generate torque. So we can do an expression for sigma tau. Sigma tau, let's make it 0 because this object is not rotating. And then you've got three torques here. These two would cause, with respect to this point, clockwise rotation. But if you had something pushing up here, that would try to cause counterclockwise rotation. Now, nothing's going to rotate here because they're in rotational equilibrium. But that's our positive torque. This is negative, this is negative. And if we look at it, we can do the math here. So we'll start out with the positive one. N2 is completely unknown, but what I do know is that this is 5 meters away from the pivot point here. Our person's force is known. It's minus, because it's going to be our clockwise torque. 735.75. And he is exactly 3 meters away from our pivot point here. So, 3 meters there. And then this one, the board itself, 490.5. that's got to be 2.5 meters away from here. So if we solve really quickly, let's see what we end up getting. You know, if I were really smart, I probably would solve this ahead of time so we don't have an awkward silence while I type crap into the calculator, but it is what it is. Here we get N2, 686.7 newtons. Now, if this is correct, and I actually don't know if it is because I screw up typing things in the calculator all the time, but if it is correct, I can take this number, put it into here, and then I can now solve for N1. Now, you could have solved for N1 directly by choosing a different pivot point. If I chose, let's say, this to be my pivot point, that would have changed the expression entirely. It would make this generate no torque, this would generate torque, this would generate torque, this would generate torque. If I look at the expression here, I would still assume it's not rotating, so sigma tau is equal to 0. But if you take a look here, this would cause clockwise rotation, and these would now be counterclockwise rotation. So let's make the positive ones first, 490.5. That's 2.5 meters away. This guy, my picture might not be the best drawing here, but if that's 3, that's 2. So this would be 735.75, 2 meters away. Notice, the magnitude of his torque changes when you redefine the pivot point. And then N1 is unknown. I do know that it's negative, and I do know that it's 5 meters away. Theoretically, if I didn't make a mistake here, however you solve for N1 here should match this number here. So I'll encourage you to do that on your own. Right now, the expression looks good to me, so if the math works out, hopefully we've done something right here.